Good morning, students. Welcome to the class on postulates of quantum mechanics. The development of quantum mechanics is based on certain basic postulates which are neither proven nor derived, but they provide a convenient framework for the further development and applications of quantum mechanics. They are universally accepted statements which are not proven yet. They are also known as axioms, meaning non-proven true statements. That is a truth which doesn't need any further proof because it is obvious by itself. There are 5 different postulates of quantum mechanics. We will see one by one. Postulate 1, which is known as the wave function postulate. That is, it states that the state of any quantum mechanical system is completely specified by a function psi that depends on coordinates of the particle and time. And this particular function psi is known as the wave function or state function. So it is a function which describes all the properties of a system, and it is depending on the coordinates of the system. For example, if it is present in the three-dimensional space, it is depending on the coordinates x, y, and z coordinates of the space and time t. So it is this wave function which determines or gives all the properties of a function or all the properties of a system. So when you study about wave function, there are different conditions. That is a particular system. When we consider a particular system, it will be having a large number of wave functions. But the function which can be accepted requires certain conditions to be satisfied. And such functions are known as acceptable wave functions. So we will see one by one what is an acceptable wave function. An acceptable wave function is one which satisfies the following conditions. It should be finite, it should be continuous, and it should be single valued at all points. We will study each in detail. Finite means there should be a fixed finite value for a wave function. It cannot be infinity, it cannot be zero. So only such functions will be acceptable. It should be continuous. When you plot the function, it should be obtained as a continuous curve. And also other third one is it should be a single valued at all points. That is, for a particular value of the function, it should have only one value. It shouldn't have more than one value. So if all these properties are satisfied, and we call that function as acceptable wave function. And also other properties of wave function as its orthonormality. That means it should be normalized as well as it should be orthogonal to each other. So normalization condition and orthogonality condition will be less dealt with in the next section. So this is the first postulate, which is wave function postulate, and we will be studying the different properties of a wave function. Postulate number 2. This is known as operator postulate. It states that to every observable in classical mechanics, there is a linear Hermitian operator in quantum mechanics. That means any measurable dynamic variable of a system, we call it as an observable. So for every observable, every property, measurable variable in classical mechanics, there will be a corresponding operator in quantum mechanics. Then you will be getting what is an operator. An operator is a symbol of rule for transforming a given mathematical function into another function. For example, if we take the case of the operators in mathematics, for example, addition operator, that is plus. The sign plus shows that it is two numbers has to be added. But if we put a plus by itself, simply a plus doesn't mean anything. That means it has no physical meaning. But if that plus comes in between two numbers, that means we have to add those two numbers. So addition is the operation and the operator is the plus symbol. Similarly, in quantum mechanics, for every operation, there will be a symbol which shows the transformation of a particular function into another function. And such symbols are known as operators. So it itself doesn't mean anything. So if an operator is put by itself, it has no meaning. But if it is accompanied by a function, that means that particular operation has to be carried out on that function to convert it into another function. Okay. Then the notation. Every operators are represented by capital letters, alphabetical letters, capitals, with a cap symbol on its top. For example, energy, total energy operator is known as Hamiltonian operator, and this Hamiltonian operator is represented by capital H with a cap over the H. So H cap, it is represented as, or it is called H cap, which represents the total energy operator. So corresponding to every operation, there will be a corresponding operator in quantum mechanics. These are the different operators, that is, these are the particular observables that we measure in classical mechanics momentum. And the operator is this I h cross by d by dx. It is represented as p cap x. If it is a one-dimensional, we represent it as in one-dimensional, that is small p cap x. Kinetic energy, which is represented by the formula half mv square, which has this particular operator, and the symbol of the operator is E cap. E cap kinetic. In certain conditions, it will be represented as capital T cap also. Then position of this object is represented as x, and it is represented by the symbol x cap. Similarly, potential energy is represented by V, which depends only on x direction. If it is a three-dimensional function energy, we represent it by V of x, y, z. And this particular potential energy operation is represented by the symbol E cap potential or capital V cap. Then, as we already said, total energy operator is a sum of kinetic energy operator plus potential energy operator, and it is represented as H cap. Then the last one is angular momentum operator, which is coming in the case of a rotational motion, and it is represented as L cap. And these Lx represents this component in the x direction, Ly in the y direction, and Lz in the z direction. The total angular momentum will be the sum of these three, which is represented as capital L cap. So these are the common operators that we use in quantum mechanics. So for every classical mechanical observable property or observable variable, there will be an operator in quantum mechanics. Then we have already said that what is a linear, we have already defined the second postulate as a property, every observable will be represented by a linear Hermitian operator. So linear operator is one which satisfies this following condition. If A cap is the operator, it is acted upon the sum of two functions f plus g, then it should be equal to a cap of f plus a cap of g. Or in multiplication, a cap of product of CF should be equal to C into a cap of F. If these conditions are satisfied, then we call the a cap operator as a linear operator. An example of a linear operator is d by dx, because if we take d by dx of the sum of two functions, it will be equal to the d by dx of each individual function, the sum of the d by dx of each function. Similarly, d by dx of a product of two functions will be equal to this. Whereas bracket square is not a linear operator. So linear operator is one which obeys this condition. Okay. Then another property of the operator is it should be Hermitian. So any operator which satisfies this condition, that is integral psi star r a cap psi r dr is equal to integral a cap psi r cap star psi r dr. That is, star represents the conjugate of the function. So if this condition is satisfied, we call that particular operator a Hermitian operator. So according to postulate number 2, every operator will be linear and Hermitian. So that is the second postulate. Every observable in classical mechanics, we have a linear Hermitian operator in quantum mechanics. Okay, we'll study the other three postulates in the next class. Thank you.